So with rapid proto or additive manufacturing, some of the other processes and aspects of it that make it better is, so when you're making something, you really only add the material needed to make it. Okay? So we aren't wasting a lot of material. Here's an example is I got this guy right here. Okay? If you look to make the 3D on this printer, they really only use the extra material it uses is just this strip right around here. And so that is one of the aspects of 3D printing, is that there is very, very little waste. Where if you would think about, for us to make this, let's say out of wood, think about how big a block it would have to start with and how much wooden material we'll have to remove from the block to make that. Because you're going to have to start with a block or a board that is at least the size of the maximum dimensions of the part, and then you're going to have to go in and cut away. And so so that's really what's going on. Okay. Next, you have that when making it, making a 3D part on a 3D printer, you can have infinite number of layers. Okay? Sort of, okay? And that all 3D machines work this way. And why I say it's sort of is because you can't have an infinite number of layers of material that has a finite thickness. Okay, so the filament, okay, what is being laid down, has some sort of thickness. Okay, and so you can't, so at some point within building this, there's going to be a thickness, and that along the way you need to know that the smaller the thickness of the part, the more accurate it will be to the original CAD model, but the more time it will take to print. The thicker the material that it lays down, the less accurate it will be. Okay? Hopefully that all makes sense. You can't have you can't lay down material that has thickness and make it not have any thickness. It's just not feasible. But that's what all happens. Okay? Some of the other nice things about rapid prototype or additive manufacturing machines is that they're able to use different materials. Okay? And so that's where some of the changes start occurring. So for example, and these are just some of the materials. So the one that broke down because of the mice printed acrylic, okay, and it printed great prints, okay. I will say it is a great print, and for $30,000 it should, and it is a very one that you would actually find out in industry. But it is, the use of it for our purposes isn't needed, okay? Because I'm not here to necessarily teach you. I'm here to teach you what you're going to use out in industry. But the processes used with the Stratus and that the mouse one are the same, and so I can teach the processes so you can go from one to the other and learn the nuances throughout it. Okay, the Stratus and our new ones, the Artemis, okay, from Artemis, they use ABS, PLA, and PETG, and so they're using a much the accuracy of them, and this looks like an ABS or a PLA. So they use these right here. They take a lot less time than this one, but I'm going to say this one had a much nicer print. Okay. But there's also another thing that has to go on, and it depends on the machine which one it uses, okay? So you have the bonding processes. So somehow you have to get the layer that you're laying down to bond to a previous layer, okay, a previous layer, and then a next layer. So how the part does it, okay, and how different ones do it changes, okay. The Artemis and the Stratus, they both use heat, okay. They both use heat. They melt that plastic really, really fine. They lay down the next layer, and then as they cool, they combine to make the part, okay. You also have with the one, the 8, and for some reason I can't remember the name, and I'm not going to go research it. It used UV light, so it used light to solidify the acrylic to make it. I know a lot of older ones, they actually used lasers. Okay, they used lasers as solidifying it, and I cannot tell you which one. Which material it is, but I'm telling you that if you go to it and you need to do a little bit more research, to be very, very careful where if you combined a certain type of plastic with the laser that it used, it actually creates mustard gas. Okay, and hopefully you guys have heard of mustard gas. And if you don't remember the historical process of it, is mustard gas was what they used in World War I. And mustard gas kind of got outlawed from war from then on out after World War I. And how mustard gas works is the person would inhale it and then would literally cough up their lungs. Okay, and that's how mustard gas works. And I think they're really trying to move away from those type of printers. And the reason why is they also had to have a ventilation system to expel the gas, okay? The gases that it created within the manufacturing process, okay? Much like you would have to have with some sort of wood or metal, you have to expel stuff. But like with the Artemis, the one that we have up on the screen, and the F-170, they don't have to have, okay, they don't have to have the mustard, the exhaust systems built in, because the chemical reaction isn't. They're not really having, they're bonding materials together, but they're not doing it chemically, okay, where the laser did it chemically. And so that is why additive manufacturing gained more power, okay? And you got to remember, as we've created more and more powerful machines, things have changed. So like I said, right, the original, okay, we modeled for the form, okay? We were only worried about form and the production. So we were making the rapid prototypes. But as our products have changed, we've improved, and we've made machines with higher accuracy. They've increased the fit, okay? So we can begin to test how parts will fit together. We've also been able to change material, and we've been able to change the function. So now we have, as we've changed the conjunction of the material processing, and we've changed the accuracy, the fit, and the form, we've been able to do different things, okay? So right here, it looks like we have, one of the examples is how we are able to use a metal and a laser. So right here we have, it looks like a V3. It is an engine block, okay? We were able to manufacture a small engine block. Now, does it have all the other components needed with it? No. But in theory, okay, we have this completed engine block where we've been able to make on a printer, instead of milling or casting it, that we're able to use. So that's what's cool is now we have an engine block where if we started adding the different cams and cams, our pistons, valves, in theory, we could use this engine right here and create, make movement with it. So there was one other thing I wanted to show you with this, and I haven't said with it, and it's because I hope you guys, I really do think a lot of you should be, I think every single one of you should be college bound, whether it be the technical certificate or the post-secondary, the 4-year university bachelor's degree. But I wanted to show you kind of what I've had to go through just to do and make this. So I've created my citations, okay? These are all APA style for the most part. I don't have these hanging paragraphs. I don't have these guys over to the right. But these are just the citations that I have made for this close to 45-minute presentation about everything that goes on. I may have left one or two off, but yeah. So to make this presentation, I've had to go. Here's the first 6 citations. Here's the second 6 that I've needed to make this presentation. Okay. And this is the book, okay? So I wanted to make sure. Majority of these guys here are pictures, okay? Almost all of these here are the pictures that I use because they're not my pictures, okay? And so I have to cite them if I really wanted to along the way. And here are the last ones, okay? And so to really make this presentation, I would need to cite all these sources, okay? And it's more than just the URL, okay? I needed information in a certain way. So here are the citations for my video. Sorry. All right, guys. Thank you.